In our next example, our integral does not appear to match any of our forms from our theorem. We do not just have a square root in the denominator. There's no square root in our denominator. And then this second one that does not have a square root only has two terms, an a squared plus a u squared. We have three terms. So the first thing we're going to do in this problem is we are going to do some algebra to make our denominator look more like the denominator in number 2, the one that has no square root and only has two terms in the denominator. And to do that, we are first going to need to complete the square on x squared minus 4x plus 7. So you may remember this process from 171. In order to complete the square on this, the first thing that we do is we rewrite this quadratic. Put a plus sign, I'm going to leave a blank right there. And the plus 7, I'm going to rearrange to the last term. So I'm going to insert two blanks, one before the 7 and one after the 7. In the blank before the 7, when we're completing the square, the number that we add into this blank is always b divided by 2 squared. In this case, that would be negative 4 divided by 2 squared, which will give us negative 2 squared, which is a positive 4. So I'm going to add 4 into that blank right there. And if we're adding 4 into that blank, then to balance this equation and make sure that we haven't changed anything, in the last blank I'm going to subtract 4. So notice I did change my sign right there. We added 4 in the first blank, and we subtract 4 in the last blank, so that we haven't changed the problem. And the reason that we add that 4 in is because if we do it correctly, then our first three terms should be able to factor. So we should be able to factor this now, and we can. This expression here now factors into x minus 2 multiplied by x minus 2. I'll combine the two constants on the end, giving me a plus 3. So we have x minus 2 squared plus 3. So now I'm going to rewrite our original integral that we started with. We now have the integral of dx over, and instead of writing that trinomial, I'm going to rewrite it as what we have at the bottom, x minus 2 squared plus 3. I'm going to switch the order of that and just put 3 plus x minus 2 squared so that it looks more like what we have in number 2. Because now that would suggest that our a squared is equal to 3, so that our a is the square root of 3, and that our u is x minus 2, because we have x minus 2 squared in place of u squared. So if u is equal to x minus 2, then our du is simply dx. And now we can start our substitution, because we can replace dx with du. I'll replace 3 with the square root of 3 squared, and the x minus 2 squared is simply our u squared. So now this integral looks very much like the integral in number 2, and we can work on filling out the right-hand side of this, which tells us this is equal to 1 over the square root of 3 multiplied by arctangent of u over a, which is the square root of 3, plus c. And the last thing I will do is sub back in what u is. So we have 1 over the square root of 3 multiplied by arctangent of u, which is x minus 2, divided by the square root of 3, and we have our plus c on the end. In example 5, we again want to integrate something involving inverse trig, and we will need to complete the square. So we start off looking for the area of the region bounded by this function, the x-axis in these two lines. I will give us a sketch of what that graph looks like. This is the graph of our function, f of x, and we want the area between x is equal to 3/2, which is right there, and 9/4, which is about right here. So we are looking for this area right here. Now we know how to find the area under the graph of a function between two x values. Generally speaking, that area is equal to the integral from the lower bound of 3/2 to the upper bound of 9/4 of our function, 1 divided by the square root of 3x minus x squared. Now when we start to integrate this is where we're going to have to use a little bit of algebra in addition with this theorem that we've learned in this lesson. Because I cannot integrate this using u sub, since what we have under the square root has a highest exponent of 2, and there is no exponent of 2 that shows up in the, there's no exponent of 1 that shows up in the numerator, so we couldn't use u sub. This also does not match any of our forms that we have from our theorem. So in our theorem, we have two forms that do have a square root in the denominator, but in both of them, it's either a squared minus u squared or u squared minus a squared. When we're looking to match forms, a is only a number, right? A is just a number. So I can't match this to a squared minus u squared because this first expression, 3x, is not just a number. So the first thing we're going to do is we're going to take the 3x minus x squared that's under the numerator, and we're going to complete the square on it. So to complete the square here, we're starting with, I'm going to write this as negative x squared plus 3x. When we're completing the square, we need the leading coefficient of x squared to be a positive 1. So I'm going to pull out a negative 1 from these two terms, leaving me with x squared minus 3x. That's my first step. Now I'm ready to start doing some algebra to start completing the square. I'm going to put a blank right there. I'll close parentheses and then I'll put another blank out here. And we'll figure out whether we're going to be adding out there or whether we're going to be subtracting right there. So we still need to fill out if this is going to be plus or if this is going to be minus. So the number that we put into this blank here is always b divided by 2 squared. In this case, our b is negative 3. We have negative 3 divided by 2 squared, which is a positive 9/4. So I'll add 9/4 in that blank. Now when we put 9/4 in that blank, remember that we have this minus sign out in front that's being distributed to that. So that's really a negative 9/4. So to balance that out on the outside, we're going to need to do a positive 9/4. So now, if we have this set up correctly, the quadratic on the inside of the parentheses should be able to factor, and it can. It factors into x minus 3/2 multiplied with x minus 3/2. And I'll bring down the plus 9/4 on the outside. Now, if you have any questions about how we have completed the square on this, please do let me know. I can post some additional practice on just going through this process here, completing the square. So completing the square is not a calculus topic, it's an algebra topic, but we have to be able to do it to do the calculus here. So now we have, by the way, one more hint I will give you is that when you get to this step and you're trying to factor and fill out these two sets of parentheses, they should always be the same thing, right? Because our goal is for this to look like something squared. So it should always be the same thing inside those parentheses. And the number that you'll use, like the negative 3/2 that I used, is always going to be this number. Whatever number you squared to get the number that you added in when you were trying to complete the square. Okay, so now let's go back to our integral. We have completed the square, so I'm going to rewrite our problem. Area is the integral from 3/2 to 9/4 of 1 over the square root. I'm going to replace the 3x minus x squared with what we found when we completed the square. We have 9/4 minus x minus 3/2 squared. I just wrote this and put the 9/4 in the front so it looks more like the version we have from our theorem. Don't forget the dx on the end. And with this 9/4 minus x minus 3/2 squared under the square root, that looks most like our arc sine version, where we have a squared minus u squared. Remember that a should always only be a number. So that suggests that our a squared is 9/4, so that our a is 3/2, and our u is x minus 3/2, so that our du is simply dx. So now we're ready to rewrite our integral with our substitution. In the numerator, the 1dx is just getting replaced with a du. In the denominator, under the square root, the 9/4 I'll just write as 3/2 squared. And from that we are subtracting u squared. Now notice that I have not put limits on my integral because we have limits of 3/2 and 9/4, but these limits are x limits. And now we are working with a u integral, so I'm going to change my limits. I had x limits of 3/2 and 9/4, and I want to change them to u limits using the fact that u is equal to x minus 3/2. Same substitution that we have there. So when I substitute in x being equal to 3/2, I get u is equal to 3/2 minus 3/2, which is 0. So the new lower limit for the u integral is 0. And when I substitute in 9/4, I get u is equal to 9/4 minus 3/2, which is equal to 3/4. And so our new upper limit for the u integral is 3/4. So I changed my limits. You don't have to change limits, but that is one way that we could do it. So now let's go ahead and fill out our integral using number 1 from the theorem. So this is equal to arc sine of u over a. I'm not going to put a plus c because we have a definite integral that's being evaluated from 0 to 3/4. Now because we did change over to u limits, I do not need to sub back in what u is. I will go ahead and replace this a though with 3/2 because that we do know. So we are left with arc sine of 3/4 divided by 3/2. That's from plugging in the upper limit of 3/4. And from that we subtract arc sine of 0 divided by 3/2. So we have arc sine of 3/4 divided by 3/2 gives us 1/2. 0 divided by 3/2 is simply 0. So now we are back in 172, our trigonometry class, where we are evaluating inverse trig. Arc sine of 1/2, we're looking for what radian measure on the unit circle that's between negative pi over 2 and pi over 2 has a sine value of 1/2, and that is pi over 6. And the radian measure on the unit circle that has a sine value of 0 that falls between negative pi over 2 and pi over 2 is 0. So arc sine of 0 is just 0, and we are left with our final answer of pi over 6.